My name is Johnny Chen, and now I'm going to present my research project. My topic is rule-based task scheduling in cloud edge computing for energy and resource utilization optimization. And we have 6 parts for my presentation. They are introduction, methodology, implementation, evaluation, results, and conclusion. First, I want to introduce the background and motivation. We see that more and more smart devices now, and so we can have big problems with using cloud systems. Their systems are getting overloaded, and energy and resource distribution imbalance, and huge delays in processing data. Nowadays, we have 3 types of challenges. The first is task distribution, that we don't have good rules for organizing tasks, and resource management, that how to decide where to run tasks and think about how powerful each is, and simplicity and complexity, that using fancy AI methods or using basic rules. So my research question is that what basic step can help save power and make resource management better when handling everyday's task in cloud edge computing environment? So for my research, I have 4 part solution. That first is use the Prometheus as a tool to monitor system metrics, and the second is apply the simple decision rule to decide which task should go, and third is execute the task migration to for the task move between cloud server and edge server. The next is measure performance, how better the new system compared with baseline and scheduler. This is my system architecture. This architecture can keep track of everything and make sure that the task runs smoothly between cloud and edge. And this is my methodology. I have a 6-part methodology. The first step is to set up Kubernetes cluster and then deploy container applications. And the third is simulate various world nodes and then connect performance metrics and apply scheduling rules. Last is compare results against baseline. I have the main technologies. They are the first is Path and Flask. They are the main tool to building the service. And the second is Docker. Docker can build program and everything and make everything inside the package. The main tool is the Kubernetes. Kubernetes has a good smart manager and take care of running containers. The monitoring tool is Prometheus and Graph. They work together to watch how system runs. And obviously, I have 4 parts, 4 rules for my research. The first is CPU-based task migration, that the system move task to edge when the cloud reach 14 or 15%. The second is location-aware scheduling, that system send to request to the nearest server. The third is content. It's about content. The popular content can stay stored on nearby devices. The last one is dynamic resource scheduling, that when the server get busy, the Prometheus, the Kubernetes can automatically create the new pod to handle the node. For my research, I get 2 metrics. The one is CPU usage, to look how how work gets shared between cloud and edge, and memory usage to see how storage space gets used. And for my code part, I have 4 rules and 4 files here, and they are all about the configuration file. And I'm going to show the first rules, and other rules are the similar patterns. I'm like to show the first rule is task migration, and for the task migration, the first one I want to start the service, and in the browser, and I would like to start this service. And this is for the baseline, and I'm showing the baseline. The next thing I will show the scheduler result. I'm starting the service is for the schedule. It's for the baseline, and I use two. It's the Grafana is the is for the graphs connection, and Prometheus is for the query and alerts. And for the alerts, for this alerts, it's for the scheduler. I will explain later. And I just started the service, and you can see it here. I created 4 dashboard for each rule, and the first one is task migration dashboard. You will see it's approximately it's already there, and you see it's a baseline, and I will show the scheduler result, the situation after I use the scheduler. The scheduler I want to display is that I used the rule like the alert. This is a alert when the CPU usage reaches above 15%. The Prometheus will show the result in the browser. It's like this. This is the alert in the browser. It will show the red color, and automatically the Kubernetes will delete the old pod and create the new pod in the edge node, and to run the service. And we will show after the scheduling and the differences between the usage and the memory rise. And now we need to look at the scheduler, use the scheduler, and we need to start the service now. And then start it. And we need to check the usage, CPU usage, to look at how it's look like. The Zuner tells us we need to reach the 14%, and the scheduler will toggle, so we need to wait for it to reach the 14%. It's 14% now, and then in the meantime, we need to focus on this CPU usage graph. In the meantime, we can look up the memory usage, how it look like. It's like always keep 14. 14, but it's 14%. We can look at this schedule. It's almost it's a little delay, but it's mostly a rising pattern, pattern, and then we can look at this Prometheus alert to trigger this rule. Oh, it's fire now, so it's the alert is action. And look at the code part, and after the scheduler, the old pod was deleted and the new one is created. And look at the graph, and before it's up to 14%, and now it's going down, and the CPU is going down 13 and 20. And when we look at the memory usage, for the memory usage, it's minimum kept similar, but it's with the scheduler, it's a better distribution between the nodes. So this is rule 1 implementation experiment, and for a list of other rules, it keeps the similar patterns. So that's it. And I will explain the rest of the rules. This is a load balancing rule. It's a similar patterns as it uses the same service as the first one, task migration, and just create the deployment for the pod deployment Kubernetes resource for create the pod on the code load, and the deployment for the service pod on the edge load, and the destination rule to put the nav on the version of the service, and use the gateway and the service for the pod, and mutual service like the route traffic, like if the user uses the header like this, and it will go the request traffic will go to the edge one, and otherwise is the traffic request will go to the cloud one. So it uses the ISTIO to complete the scheduling, and the last one is the content, is the product content. I create the content is the product service content, like this one is for the 101 for the hard protect, and otherwise is the not hard protect request. And you also make it the container, and then create the deployment for to create the pod for the container, and the edge on the code load. And for this one, it's also the same, use the deployment resource to create the pod of the container on the edge load, and also use the ISTIO and gateway to route the traffic. And the next one is the next one is also another scheduling, use the HPA. It's the HPA. It's the horizontal pod or auto scanner. It will automatically create the pod on the load based on the CPU usage. Is this skill, and also use deployment resource to create a pod on the cloud load, and to create the load on sim node on the edge load, and use the destination rule to put the enable, and when the rule for this one is when the CPU usage and edge node usage reaches the above some 20%, it's like this number, and the service is busy, and this configuration file will automatically create a new pod and to run the service. So after this experiment, we will see like get and use the Grafana to see. Yes, just like this, to get the graphs and baseline and scheduler patterns. And the patterns like this is the CPU usage, like baseline is up, after the scheduler is down. It is for the row 1, and for the memorizing it's keeps similar. It shows and this is row 2, and we can see, so it's up amongst these 14, but for this one is 20, and the memory is the same, but it shows the better resource distribution. And for the experiment 3, it's also like a little down after the scheduling. Yeah, so but the memory is keep the same. Like the first one is automatic scanning, like it's a 14, 13, and it's a 20, and the memory is similar, but it shows a better distribution because uses the scheduler is better balanced for the memory in the system. After the whole rule implementation, I get the overall performance improvement, that 15% CPU reduction, and the memory is keeping similar, and but it shares much better because of the scheduler. It has the better distribution, and obviously I use 4 basic rules to schedule the task to make the system running smoothly. However, we have some limitations and challenges for it. The first is it's a fixed rule, so they have the limitation, and the parameters make the system take a little time, so there is a overhead time. The next is simulation, that the research simulate is experiment space instead of the real, so there is a difference. Another is about rule optimization, that how to set the best limits for the rule. It needs changes for different situations. This is a reference for the whole presentation. 1, 2. We come to the conclusion now. The task shows that the basic rules can make the cloud and edge system work better, use for resource and reduction of CPU usage, and the similar and better distribution of memory space. So this result confirms that basic rules turn out to be good enough to speed up things and cut down the power use. So that's all for my presentation. Thank you.